So next, cloud clustering was built on Windows Azure. So and it's very tied. It's closely tied to its features, and it takes maximum advantage of them. So here's an overview of Azure's features. So Azure, first of all, of course, it's a Microsoft's cloud platform. And so my goal this summer was to explore how suitable Azure is for data-intensive research by building a large-scale clustering algorithm on Azure. And this is the first step towards building a machine learning toolkit that runs on the cloud. Here's some key terms in Azure that I'll be using throughout the talk. First, instance. An instance is a virtual machine that runs, it's managed by Windows Azure, but that runs user code. Blobs are Azure's way of storing named files. So they support random reads, but writes must be done in blocks rather than randomly. So this modifies how things work. And so blocks are uploaded in any order to this blog, and then they're committed in one final constant time operation. Queues are a way of reliably delivering small messages between instances. And tables store queryable lists of entities, which are, so tables are not relational databases. So you can't do any cross-table queries. They're very scalable, flat lists of entities. Okay, so clustering was the problem that I was actually attacking here. So here's some background into that. So clustering overall is assigning a set of data points into similar subsets. It's heavily used in machine learning and data mining. So there are plenty of examples. I mean, it's all over the field. But here's just one. So this is Bing News. Every article has a link to more stories here that takes you to a list of news articles about the same topic. So Bing News uses clustering to group articles together so that it can show these kinds of lists. And here, notice that Bing News gets maybe 1 million new articles each day. And so clustering all these articles into similar subsets is a difficult problem. And that's why we need parallelization to take care of that. Well, first of all, one very popular clustering algorithm is called k-means. So the name comes from the fact that it groups data points around k-mean points, such as this function is optimized, is minimized. This is the sum of the r² distances from each point to the cluster's mean point. And so we start with a set of data points and a value for how many clusters to group them in. Let's call that k. In this case, k is 3. So I'll just quickly step you through a visualization of how k-means runs, but because of time, I won't go into very detail of that. But so here's our human known target clustering. Here's what we actually want k-means to give. And so it starts by initializing random centroids, k random centroids. It assigns all the points to their closest centroid. This is first passive clustering. Then it recalculates the centroids by moving them to the average or the mean of the points that they own. It does the same thing as before. It assigns the points to the centroids using the new centroids. So the clusters are looking a bit better now. It keeps iterating over this. So recalculate the centroids again, and it keeps recalculating, assigning, and looping until it reaches the stopping condition, which is where no points move from one cluster to another. That's the stopping condition.
So quick question. K is an input.
K is an input, yes. So actually, yeah. So choosing K is very important for the user. In our case, it's just a given. So next, here's some prior work that's related to cloud clustering. So k-means, first of all, has been built on a variety of platforms. MapReduce, there's Dryad. There's even a fairly simple Azure system called CloudClustering. So all of these prior work help give insights into the basic structure of cloud clustering, which is our Azure k-means implementation. So cloud clustering builds off of this knowledge, and additionally takes advantage of Azure-specific features to get the maximum performance. And the deeper goal with cloud clustering is to gain experience in building data-intensive algorithms on Azure.